Hello everyone, welcome to Rainbow Science. We are in college farm. We are speaking with Julian Barbour, theoretical physicist who studies foundational issues in physics. And we are going to discuss some of his ideas from his recent book, Janus Point. It's my first live episode. It's not recorded through Zoom. We are in college farm. It's near Pandora, and let's start with a sort of history of this place. How you discovered paper by Dirac, how it influenced you, and how being in this place has to do with what kind of physicist are you, as you write.
I was studying, I was going to do a doctorate in astrophysics in Munich, and one weekend in October, that was in 1963, I went with a German student friend, and we were going to climb the Watzmann mountain in southern Bavaria. And I was reading on the train there, I was reading an article in the local Munich newspaper, the Süddeutsche Zeitung. And it had an article about a very remarkable article by Paul Dirac. So Paul Dirac was the great British physicist who made many huge discoveries in quantum mechanics in the 1920s and early 1930s. And Dirac had written, he just wrote one popular science article in his life, and that was for the Scientific American in May 1963. And there was an article about this in the newspaper, which I read. And it very struck me, because Dirac had wanted to make a quantum theory out of Einstein's general theory of relativity, this absolutely fabulous theory of gravity. And to do that, Dirac, instead of representing it as a space-time theory, where space and time are fitted together in a block, he had wanted to, in order to make it into a quantum theory, he wanted to represent it as a dynamical theory where things change in time into something different. And he made what was for him a very surprising discovery. So his great principle was to have only the things that are really physical, not just to do with the way you represent them. So there's a distinction between what are called gauge degrees of freedom, which are just representational, and physical degrees of freedom. So he wanted to get rid of all the gauge degrees of freedom and just have the theory purely in terms of the physical degrees of freedom. And then he found he could only do that if he broke with the great founding tradition that Einstein had in relativity theory, that there's no unique definition of simultaneity. So Einstein, this was what all relativity was about, that there's no unique definition of simultaneity. Even on the smallest scale between you and me was not meant to be. And he found that the only way to do that in Einstein's gravitational theory, which was not the original special relativity that Einstein had created, which does not have gravity in it, when gravity comes in, he found that you had to restore simultaneity. And in fact, if you go back to the scientific paper he published in 1958, you'll find that it's about 9 times he says that he has to restore simultaneity, and twice he says it he's put it in italic to really emphasize the point. So this made a great impression on me, and then so we got to the hut in the mountain, and we went to sleep. And then when I woke up at sort of 6 o'clock in the morning, I had a horrible headache, and I went out for a call of nature, and I could see Orion, bright stars in the sky. But I said to my student friend Jürgen, there's no way I'm going to climb that mountain. So I took to aspirin and went back to bed. Then I woke up feeling much better. So then if Dirac says we've got to restore simultaneity, this is very radical, what is time? So that was back in October 1963. It must be almost in another 10 days or 5 days, it will be exactly 60 years. That happened. So then I thought, well, what is time? And I've been thinking about it ever since.
Your latest book, Janus Point, goes against consensus that universe is going towards disorder, and it goes towards disorder, but you claim that universe order actually grows in the universe, and you, according to your theory, initial conditions of the universe was actually low entropy. Could you explain how your theory differs with these assumptions?
Yes, well, this goes very much against tradition which was established in 1850 with the discovery of the laws of thermodynamics. So the laws of thermodynamics came out of the study of steam engines. There was a really wonderful little book published in 1824 by Sadi Khan, a young Frenchman. And the title of the book was on the motive power of, I think it's fire, not even heat. And he was very interested. He said there's no doubt about it, the English invented the steam engine. And that's where the great strength of the British nation is, even more than its navy, he says. But he says, but the understanding of the steam engine is very limited. So what he wanted to do was establish what was the maximum efficiency that a steam engine could run at, because they burnt a lot of coal to do things. So he wanted to work out what's the maximum efficiency. Now, he didn't succeed in finding an exact value, but what he showed was that there's a temperature where the steam in the cylinder starts off because it's heated from the furnace, and then the cylinder expands and it does work. But then you've got to get rid of the last bit of heat. You have to put it into a cold reservoir to get the cylinder to come back again, because you want the steam engine to run continuously. And so first of all, he got two things which were quite right. One was that you can never use all the heat. Some has to be wasted. It has to go into this cold reservoir. And the other one that he did get exactly right was that the maximum efficiency would depend upon the difference of the temperature between the two temperatures. But the exact amount he couldn't determine. And very few people took any notice of this paper for quite some time. A Frenchman did do important work and actually got a diagram, a famous diagram, which showed illustrated Carnot's ideas. But then in 1849, this remarkable student in Scott, William Thomson, he in Scotland, he had got to know Carnot's work, but Carnot made one serious mistake. Carnot thought that heat was a fluid and it couldn't be destroyed. And he had an analogy that a steam engine works because it's like a waterfall. The water is high up and then it falls down. And he thought that the analogy with heat was at the top of the waterfall, the heat was at a high temperature, and then it was at a lower temperature lower down. That's the one thing he got wrong. So in 1849, William Thomson published a very important paper, drew attention to this work of Sadi Khan, but he himself said he thought that it was too soon to throw away this idea of heat. It was called caloric, when we had the idea of heat as a fluid. But anyway, he published this paper, but then very quickly, immediately, the German Rudolf Clausius picked up this thing and decided that there was just one mistake in Carnot's work, that when the steam engine does work, as it does that work, the heat is literally destroyed. But there's still some heat left, and that has to go into the reservoir so that you can start the cycle again. So that was his very important insight. And he already then realized that there were two fundamental laws in thermodynamics. One was the conservation of energy, and the other was that, well, what he said was that the heat never flows spontaneously from a colder body to a hotter body. It always flows spontaneously from a hotter body to a colder body. And that became the foundation of the second law of thermodynamics as he formulated it. And that's all in his paper in 1850. And at the same time, Thomson, meanwhile, had come to the same conclusion, and he didn't publish it quite as soon as Clausius, but it is recognized that they independently discovered the two laws of thermodynamics. But what Clausius then went on to develop the atomistic interpretation of heat, that heat is really lots of particles moving in random directions, and the faster the particles are moving, the more amount of heat there is. And very brilliant work, Clausius developed what he called the notion of entropy. He called it entropy. He originally talked about something called the transformation value, which is not a very good expression. So he decided he would find the proper word. So he went to Greek, the ancient languages, and tropy was transformation in Greece. And then just to make it sound like energy, he called it entropy. That's the two fundamental quantities of thing. And so he then said, there are two fundamental laws of the universe, he said. The energy of the universe is constant. The entropy of the universe tends to a maximum. And meanwhile, the theory of molecular and atomic motions underlying what heat is suggested that an increase of entropy corresponds to an increase of disorder, because a very simple example is you have a box. We could have it here in front of me here, and I go down to my freezer and I get out a cube of an ice cube and I put it in the box in the corner. And the air in the box is at a certain temperature. Well, bit by bit the ice will melt, it will become water, and then the water will evaporate, and then the water molecules will fill the whole box uniformly. Now at the start of the procedure, the water molecules in the ice, they're in a very precise, rigid lattice form, very highly structured. And then when it's all evaporated and a uniform distribution, all the water molecules are moving in a completely random direction. So you've gone from order to disorder, and you can wait till the end of the time. It will never go back to the ice. So that's the story that people have believed, and it's perfectly true for ice in a box since the discovery of since Clausius's paper.
The latest data from James Webb Space Telescope indicated that even early stages of the universe, there are a lot of galaxies, and standard model of cosmology didn't expect so many galaxies and complex structures at the early stages of the universe. And that leads me to the question, how universal is second law of thermodynamics on cosmological level, and why were scientists misled is not the right word, but why did they do for a long time that second law of thermodynamics can be applied to the whole universe?
So it's certainly true that for a very long time, and still to this day, the great bulk of scientists think that the second law of thermodynamics and growth of entropy applies to the whole universe. Now, there's a lot of mysteries about modern cosmology. In one way, it's an incredibly precise science. On the other hand, these very precise results have turned up with a great mystery. So it is, I would say it is possible that the current view is correct, that in some senses you can define an entropy of the universe, and that it is increasing. But first of all, the great problem is that the universe is certainly not in thermodynamic equilibrium now, otherwise we couldn't be talking to each other. I mean, nothing could be further from thermal equilibrium than you and me talking to each other as we are now. So already one of the great early people who did very important work in the study of thermodynamics and entropy was Ludwig Boltzmann. And one of his explanations for why, so he believed the second law of thermodynamics, but one reason why you and I can talk to each other was that the universe might have started with an extremely low entropy, which has been increasing ever since. And that's still the most popular explanation of phenomena to this day. Richard Feynman, the really very great physicist, when was it, 30, 40 years ago, he said that the only way to explain the second law of thermodynamics and that we can talk to each other, that the universe is not in equilibrium now, is to say that you must add something, you must add to the known laws of dynamics some extra thing which doesn't follow from the laws of dynamics, or laws of nature, which says that the universe for some reason started in a very ordered state and has since become more chaotic. This is a view which Roger Penrose supports, and the philosopher of science David Albert has coined the expression the past hypothesis. So the past hypothesis is that there was some very special condition in the past of very great order. However, that actually is in very strong disagreement with all the main observations we have. If you look back, so it's what's called the microwave background, the cosmic microwave background, this very low temperature that permeates the universe. The furthest back we can see, the universe was incredibly uniform, and at least the matter was in thermal equilibrium. And since then, structures have formed. I've not been following all the observations that have come from the James Webb Telescope, but there's no doubt that structure has been getting richer and richer ever since the Big Bang. So that seems to be completely in disagreement with the second law of thermodynamics, which is meant to be some physicists say it is the most fundamental law of the universe. So the one explanation that people have is that, so this is very popular with Roger Penrose. Roger Penrose has argued, he says the matter can be in thermal equilibrium, but you have to take into account gravitational entropy. And Penrose's conjecture, his past hypothesis, is that at the start, at the Big Bang, for some unknown reason, the gravitational entropy was very low, but the matter entropy was high. And that means that there's still a huge amount of entropy that can increase. Now that may be right. I'm personally myself skeptical about it because I think there's an alternative explanation. So that's the situation at the moment. I suppose Roger Penrose's ideas are the most popular at the moment.
complexity and ordered and complex structures is becoming popular interdisciplinary field of inquiry nowadays. But like with many other central concepts in science, like information, life, consciousness, etc., it is hard to define. There is no consensus. Some people, I have listened to the podcast recently that complex systems are simply quasi-teleological, telenomical, end-oriented. So others define it other way. But when I read about your definition, mathematical definition of complexity, it provided sort of simplicity, starting with a very simple system, and gradually it evolves into complex structure. Could you explain your definition of complexity?
Yes, well, perhaps I should first of all say that it's now 9 years ago a paper was published by myself and my two main collaborators, Tim Kozlowski and Flavio McCarty. And what we discovered is that if you just take Newton's theory of gravity of point particles interacting with each other, it turns out that there's an arrow of time completely unrelated to entropy, and in fact it's an arrow of increasing order. And this comes straight out of the Newton's laws. So, and in fact the key discovery, which was very important for me coming to these ideas, goes right back to 1772, so this is now 250 years ago, 251, by the great Italian-French mathematician Joseph Lagrange. And he was studying what's called the Newtonian three-body problem, which is, what he was thinking about was the problem of the Earth and the Sun and the Moon and their mutual gravitation. And he showed, so there's a quantity which measures the size of the system. It's called the n-body system, but it would be the three-body system. So there's a quantity which measures the size, how big it is. And what Lagrange showed was that if the energy is either exactly zero or it's positive, it's not negative, that's a separate situation. But to require the energy to be positive or not or zero is not a strict requirement. What he showed then was that if you imagine a Newtonian timeline, here's the past out there, and there's the future out there, and then you look at what that size of the system is doing, well, he showed that in the distant past out there, it was infinitely great. And as time, Newtonian time passed, it comes down steadily, it's always decreasing, down to a finite value in virtually all cases, and then it increases again to infinity all the way up there. And that central point there is what I call the Janus Point, or you can call it the Janus Point. Some people call it Janus, some people call it, because of January, I call it Janus. But to talk about the size of the universe, we're inside the universe. To talk about that size, you really need a ruler outside the universe to say how large it is. So we can only, within the universe, we can only see how the separations between the particles change, how the structure of the system changes. And what we realized is that there's a very interesting quantity, which we call the complexity, which is a measure of the structure, and that at this Janus point, it tells you how the particles, whether they're uniformly distributed or clustered. So it's a measure of variety or complexity. That's why we call it complexity. And what we pointed out, which should have been obvious, and I think lots of people who work in the field realize that, was that at this Janus Point, it was at its most uniform, the distribution of the particles, and the particles would be moving randomly in different directions. But then as you go in both directions away from the Janus Point, structures form, they get more ordered. And then particularly interestingly, what happens very typically is that two particles get bound together and they form what I call a Kepler pair. So Johannes Kepler discovered the famous laws of planetary motion in the early 1600s, and so you have these pairs of particles which are going around their common center of mass, and so they form a Kepler pair, and then a third particle, there were just three particles, a third particle goes off in the opposite direction. But also these Kepler pairs can form when there are thousands of particles, any number of particles, Kepler pairs will form. But then these Kepler pairs are extraordinarily interesting because every time they complete an orbit, that's like a clock ticking. So that's a clock, they form a clock. Then in addition, they have an elliptical orbit, the length of the major axis, that's a measuring rod. And then moreover, they point in a certain direction. So when you go away from the Janus Point, at the Janus Point, it's already pretty chaotic. But when you get out here, you find these Kepler pairs, which are incredibly ordered, because they're all ticking, and the clocks are not all going at the same rates, but the ratio of the rates gets ever more constant. The lengths get all more constant, and they're all pointing. So this one over here is pointing this one, that one's pointing that way, and we could have thousands of these Kepler pairs, all making this incredibly rich ordered structure. Well, that is the complete opposite of disordered brain. So this makes me very skeptical about things.
Natural scientists, physicists, many physicists, and biologists too often ignore history of science. They learn as history of science in introductory chapter, they later just equations and current state of science. But when I read about your arguments, it's like people who developed thermodynamics had no idea that the universe was expanding. They discovered it later. So will you explain that argument why expansion of universe contradicts universality of second law, and also in general your views on how history of science is important for practicing scientists to read about?
I think certainly the history of science is quite important for many fields of science. I think it's possible in the case of entropy that it's hugely important because the key thing that I already mentioned, that thermodynamics came out of this very wonderful work by the Frenchman Sadi Khan, published in 1824, and it's all about steam engines. And the steam engine, the steam must stay in the cylinder. If the steam escapes from the cylinder, the steam engine stops. And so thermodynamics, so what's called phenomenological thermodynamics, where you don't have an underlying theory of what heat is, you're always dealing with a system in a box. You can increase or decrease the size of the box. If you decrease it, the pressure increases and it will get hotter. And you have various laws there that govern how the state of the gas in the box changes. And that's called phenomenological thermodynamics. And then, when Clausius did this wonderful work where he defined entropy, he imagined that the state of the gas in the box is always changing very slowly and very reversibly. It was wonderful work by Clausius. So it's very delicate. You have to imagine that the box is slowly getting bigger, and while that's happening, it can absorb heat from outside, but then, so that's called that's which way do I understand? That's isothermal, I think. And then you have a case where it's not in contact with a body outside, and it sort of goes round in a closed loop. And you have all these relationships, and that sort of process underlies Clausius's original definition of entropy. But then you get the atomistic explanation of it, which had started before Clausius, but he was the first person who gave important results. Then you had the great Scottish physicist and mathematician James Clerk Maxwell, who came up with what's called the Maxwell thermal distribution. That was then followed by Ludwig Boltzmann, and then a bit later on, James Millard Gibbs in the United States. And in all these cases, when you look at their papers, they talk about particles that bounce into each other, either elastically or inelastically, but they're in a box, and they always bounce off the walls of the box elastically. And that's critical, because if the box isn't there, when I was talking earlier about the ice cube evaporating and the water molecules filling the box uniformly, if it wasn't in a box, the water molecules would spread out. And if this was happening in space, they'd disappear out into space. So you wouldn't get what's called equilibration. So I think this has just been forgotten by people. So thermodynamics was discovered in 1850, the expansion of the universe in 1929. So that's all just 79 years later. So can you expect the same things to happen in such a situation? So let me just say, mathematically, what you distinguish between this in mathematics is something called the phase space, and if you have and the solutions can either explore what's called a bounded phase space or an unbounded phase space. Well, when we're talking about the molecules in a steam engine, they can only explore a bounded phase space. But if there's no box and they can do that, it's an unbounded phase space. And I just think these situations are just completely different. And then the simplest model, we've already been talking about Newtonian gravity. The simplest example where that's different is actually in Newton's theory. So we've already talked about the three-body problem, but what is the earliest mathematical problem is the three-body problem and an n-body problem, where you have an arbitrary number of particles, a finite number of particles, but an arbitrary number. So these can explore infinite space. So we must expect something completely different. Now, I think it's quite amazing that this hasn't been picked up before. I think it's just possible that I was only the second person to ask, is the universe in a box? And the first person was Ludwig Boltzmann, because he was involved in a famous debate in 1896 with somebody who became a famous mathematician and theoretician, Zermelo. If you have systems in a box, there's something called the Poincare recurrence theorem. It says that if you have a system in a box that can't escape, well, it's what's called access to bounded measure. Poincare recurrence says that system will keep on returning arbitrarily close to any earlier state that it had. That's both where the particles are and the velocities they're moving. This will go on happening forever. So that's the situation that you have in there. But that's because you've got a system in a box. If the box is gone, it's quite different. And more or less as a footnote in this famous exchange, two papers each in 1896 between Boltzmann and Zermelo, Boltzmann does say, are we sure that the universe is sort of, could it be that it's infinite and that the velocities could increase arbitrarily? But I always look out for whether people have picked up on this when I read papers in the I haven't seen any. I think it's first of all in that paper of ours in 2014 where we raised that question. So I think this is quite different. And then I've already described how different it is in with all these Kepler pairs forming. So that's very different. So the question is this: suppose you're a mathematician, and I show you some points just distributed in Euclidean space, in three-dimensional Euclidean space. These are just points. And I want you to find a pure number that's just a ratio, which tells me the extent to which those particles are uniformly distributed or clustered and exhibit structure. So I want, and I'm going to call it complexity, because it's a measure of variety or complexity. Now, it's got to be a pure number, so it's going to be two lengths, one dividing another length, because it will be a pure number. It won't have any dimensions. So there are two numbers which stand out. So you can have masses associated with this, but it's easiest to say that all the masses are equal, because all the interesting thing is in the value, is the way the separations between the things. Yeah. So there's something called the root mean square length, RMS. So what you do is you take all pairs of particles, so I less than j. So you number these 1, 2, 3, 4, 5, 6, 7, and then you take all. So if you have just 3, you take 1 and 2, 1 and 3, and 2 and 3. So this is what I less than j means, and that means you're going to add up all sorts of things. And then you just take the separations between them, so they are meant to be in Euclidean space. You add up all the you square the separations, add them all up, and then you take the square root. And that's called the root mean square length. And when I was talking about the three-body problem in Newtonian theory, that's one of the key quantities in Newtonian theory. It measures the size of the system. So is that clear? But again, to talk about that being the size of the system, you need a ruler outside. I mean, this cluster of particles has a size relative to this whiteboard, but the whiteboard is essentially the ruler. So then there's another quantity, which is called the mean harmonic length. I think I'll have to take a different color now. That's better. So then there's something called the mean harmonic length. The mean harmonic, it's up there, sorry. Mean harmonic length. Now this is actually, it's the inverse of the quantity I'm going to put down there. So this is just, again, it's the summation over all pairs, I less than j. The I less than j just means you don't count them twice. And then we just take, that is just Rij, so it's 1 over Rij. And then, so you calculate this quantity, you add up all of those things, and then you invert it. That's what the -1 means. So then, to get something which is dimensionless, is a ratio, you just take the RMS over L, mean harmonic length. Mean harmonic length. And that's a pure number. Now this is, I think, an extraordinarily interesting number. So how do you measure something? Well, you take a shorter ruler and see how many times it fits along the length. Now this root mean square length is actually the average of the large separations. So the large separations, it's from there to there, or from there to there, and those ones. So basically, the large ones dominate, is the word they use, the root mean square length. So that's a measure of the, as it's on the blackboard, that's more or less a measure of that. It's about that separation there, would be the root mean square length. But this is really the average of the short length. So this is the average of these shorter ones here. So what you've got here is you're actually measuring the size of the system from within. Because this is not using a ruler outside. This is completely independent of where you're doing. And in fact, if you multiplied all of these separations by the same factor, this thing wouldn't change because it's a ratio. It's what we call scale invariant. That's very important. So that's the quantity you want. Now, it's a very sensitive measure of clustering, because if two particles here get closer together, this thing hardly changes, very small change. But this thing can get very much bigger because it's 1 over the separation. So although you're adding up all these things, if just one pair if it gets 0, then this becomes infinite. So if you put two particles together, this would be infinite. So it becomes 0. It becomes 0, and so this thing is going to get huge. So that's a very interesting quantity, and I would say it's a measure of complexity.
I remember from the books that there are 2 scenarios for Janus Point, where it goes to infinity or not, I think.
The root mean square length, this is the Janus point here. So the root mean square length, in nearly all cases, if the energy is not negative, if the energy is the Janus point, the root mean square length is at its minimum value, and then it goes to infinity in both directions. But at the Janus point, this quantity is more or less at its minimum, because the particles are mostly uniformly distributed. But then as you go out in both directions from there, these Kepler pairs form, or clusters form, and this thing just gets bigger. So this is an hour of time, which has nothing to do with entropy. So entropy is said to be a statistical quantity. It's you don't know where the things are, so you have to average over all sorts of histories. Whereas this is in every it's in every microhistory. This quantity grows either side. Now there's other solutions, which I think are actually the most interesting ones, where actually this quantity, the root mean square length, can become 0. And in that case, you get something, instead of that, you get a different behavior, which is more or less, it's this one here, where it starts at 0. So you don't get 2 halves either side of a Janus point, you've just got a beginning. And that's extraordinarily uniform. That's a very special initial condition. And in some senses, the distribution of the particles is very ordered, but they immediately start moving randomly. But still this quantity, so this quantity starts at a very low value, and it can start from the absolute minimum. So another interesting thing about this is that it's always positive. It's always greater than 0. And this is very interesting, but in some senses, in this sentence, if you say, and there are arguments to say that this thing should actually start there, well, you have something like a Big Bang. It's a Newtonian Big Bang, where this sort of size is 0. but the universe starts completely uniform, and then structure grows. And this is actually what we observe in the universe. And so we were saying all these different attempts to define complexity and so forth. I think this might just be the way to do it. And it doesn't require any sort of special processes. I mean, they talk about computational complexity, and then they talk about processes doing things, and then for some reason they get to a certain stage which looks complex. And they say, I mean, the typical thing that they say is you can recognize complexity when you see it, but you don't explain it why it's there. Well, the marvelous thing is Newtonian theory does it for you in very simple terms.
Yeah.
So I think
this definition also, for me, it seems to satisfy Occam's razor. It's not too complex itself. It's very precise and simple.
Yeah, I mean, it is relying on nothing but Euclidean geometry. So there are. Group theory is very important. So in group theory, you say that something is translationally invariant. I haven't said now. This is actually, this thing here, for equal mass particles, is the Newton gravitational potential. This is, so you get the Newtonian forces with a minus sign. You get the Newtonian gravitational forces if you take the derivative of that. You get the 1 upon r squared forces. So this is the Newton gravitational potential. Now this quantity doesn't change, so you could calculate it for these particles as they are here, and then you could imagine moving all of the particles all over the whiteboard, and that wouldn't change. You could also imagine rotating it. So these are called Euclidean translations. They're Euclidean translations and rotations don't change the value of that. However, if you change the scale, that thing does change. So, but when you take for this quantity, that is, so that's called a Euclidean invariant. This is called a similarity invariant. The similarity is when you add the dilatations, the increasing the size. So this is so to speak from the point of view of pure Euclidean geometry. It's the most perfect thing that you can imagine because it doesn't change. And very interestingly, the people who study the Newtonian n-body problem, they call this the shape potential. So the shape potential, what it is, it's the Newton gravitational potential, which is 1 divided by the mean harmonic length is the Newton potential, the Newton gravitational potential. So you multiply it by the root mean square length, and you get this quantity which the experts call the shape potential, or also the normalized Newton potential. And that is what you call a similarity invariant. This is any mathematician asked to find the quantity which is the quintessence of Newtonian, of Euclidean space, would come up with this thing here. And it's this thing. When you have these particles that interact through Newtonian gravity and imagine them as being representing a universe, the history of the universe, it's this quantity, the shape potential, which governs everything that's happened. It's not the Newton potential 1 upon that. So that's a very, very interesting fact. And so we'll see.
We also said that the way stars are clustered in the universe, reflect this view of complexity that.
Yes. I mean I don't think there's any doubt that over the history of the universe, the complexity has been growing. Now, another thing which is interesting about this is I've put it here for whatever it is, for eight points here. And I've calculated it also for those 8 points and suppose that that's the whole universe. But in fact, actually, you could have an infinite universe and you could just look at a large number of particles within them. So you could just take some part there. Now, if you did that for the whole universe and you looked at so there are two kinds of particles in quantum field theory. There are what are called bosons, so that's like photons, light particles, and then there are fermions, and basically we're made of fermions. And through the history of the universe, you can take quite large areas and you will see there's no question that it's the complexity which has been increasing. So any region there, it's the complexity that's been increasing.
Many scientists today, especially computational neuroscientists and cognitive scientists, believe that information is similar to other physical quantities. It is fundamental and it is a separate category. Along with matter, energy and information, they view it as separate thing. There is a famous phrase from John Wheeler, eat from bit, matter, energy from information. And the essay layers this phrase and really want to explain what was the main idea of your essay.
Yes, I'll do my best. So some people have a very extreme idea about information, that it is some fundamental thing which is more fundamental than matter and so forth. I just don't think that can be possibly right. I think you and I are made of fermions, as I already said. So I think this goes back to the difference between reductionism, where you look at things locally, they satisfy local laws, and you build up the structure of things on the large scale from putting together small things. And then there is it's the holistic view, the alternative is the holistic view, which is that you have to consider the whole. And I think there's a great, I think a lot of this goes back to Newton. So when Newton created the laws of dynamics, he introduced this notion of absolute space. Well, there's nothing in it. All the points are the same. It's just like whiteboard, but with all those symbols on it erased. And then he says a body left to itself will move in a straight line at a uniform speed. Well, there's the clock. Where's the structure to tell you that it's moving in a straight line? I can draw a straight line relative to the framework of the whiteboard there. And that's a debate going all the way back to Leibniz and Newton, a famous debate that they had. And I think people just forget the whole universe and imagine you can get rid of it. Now John Wheeler was a great scientist. He did some very important work. I was lucky enough to get to know him quite well. I met him several times. And then he had this idea, which is he was very good at coining these things like it from bit, or he was always doing it. I mean, he's the person who coined the expression black hole and so forth. So he was always looking for things. So in quantum mechanics, so the key thing in quantum mechanics, you could have experiments like is the spin of the particle pointing in this direction or that direction. So it's just one bit of information. And so Wheeler had the idea that the whole of existence was made up from answers to questions, yes or no questions. So this led him to say that something real, like us sitting here in all our glory, is made up of lots of bits. And when I looked at that, I thought, frankly, it's nonsense. It's not like that at all. That really things are. You need to define something in a context. So you can say. Let me just look at it on the come and go on the whiteboard again. So if you forget all the whiteboard, and you say this is, you say that point is Zaza and that point is Julian. Well, an answer to a bit would be that was Zaza is above Julian. Well, you can say that because it's on the whiteboard. Or you could say Zaza is further from the center than Julian, because again we've got this cluster of things from it. So that would be one bit. But you can only answer those questions because either you've got the whiteboard or you've got the whole cluster. So I think it's completely upside down. So I wrote this essay, it from bit, not a bit from it, because then once you get it, so the it is the complete structure, and the bit is, yes indeed, Zaza is higher up than Julian, or is further from the centre.
Which requires some kind of physical substrate to.
I think it's yes. I think you can put it as a physical substrate, or there must be structure, and then. After all, you and I are sitting in this room, and we're both sitting near to the far. That's a meaningful statement. The piano is over there. You're closer to the piano than I am. All of these things are meaningful in this context, and I would say that's holistic. So I'm getting more and more hopeful that the holistic way of thinking about the universe is the right way. And this really goes back to Leibniz and then to Ernst Mach, who was very holistic in his thinking. Ernst Mach of the Mach numbers. And it was Mach's critique of Newton's concepts of absolute space and time that stimulated Einstein to create general relativity. Although I think Einstein went about it in a very indirect and ultimately incorrect way. But so there's always been this conflict between holistic or reductionist things. And I'm getting more and more confident that the holistic way is the right way. So, that's how I think about it at the moment anyway.